1U protonate has a partial positive charge.
Yes.
So why would it be attracted to an H+.
I guess it wouldn't. But
So think about that. We'll look at this again during the second half of the course. We may do it in 10 seconds at that time, but we will look at it.
so if I don't know what I've got that is incorrect. Like, I got the same answer at the end.
Well, your proposal would not be as strong because you're proposing to protonate the positive, partial positive ion. Okay, guys, question?
If there's a benzene ring, how do you know in those two systems? How do you know if they're like
Well, the only thing we look at is para typically gives a classical pair of doublets in the HMR. We saw that a couple of times. Classical pair of doublets. Classical pair of doublets.
So that's how you know that it's
Well, you got to be careful because para doesn't always give this. So it's like, you know, it doesn't go both ways as well. But when you see this, it pretty much always means para. On the other hand, para doesn't always give that. Think about what I'm saying there. Sometimes students say, well, I don't see the classical pair of doublets, it can't be para. And I'm like, well, hold on, no. It could be. So, depends on which way you're going. Other questions?
Oh, can you explain coupling and decoupling?
What do you mean? We explained it
For
in class.
NMR. I just like didn't I kind of like went back and like did this
Do you have a specific question about it?
not like specific.
We spent like almost a whole class on it.
Yeah, no, it's just like something I don't understand. I'll look at it.
Well, if you have a specific question.
Awesome.
yeah. So like in this example, it was the answer was para. There was no.
Oh, there you go.
So you don't know what is substituted as a P. Like they're para. Like there's nothing to do.
In that particular case,
Or in case of substitutions, how do you distinguish?
what about carbon NMR? Because if it's para, you're going to have symmetry. So how many carbon signals for your aromatic ring? If it was meta or ortho, how many would you expect? Think about that. Number of signals in carbon NMR. Para will also give only 4 signals in the carbon NMR because of that symmetry. Where in ortho and para, you have to think about it, how many. That's why on the warm-up page, very first NMR, very beginning of the warm-up page, NMR handout. Very first page. Now I've already updated this because, believe it or not, after every lecture I'm like, well, we could have did this instead. It would have been better. So I've already updated this. And that, and this, and that. But why did I have this question here? It's because of what I just explained. If you look at the carbon NMR, now there's no para one here. I've actually added the para here. But you can see the difference in carbon NMR sometimes.
Could you show for the second one how many carbon signals?
How many carbon? Well, the answer is given on the very back page. Okay. Other questions? Okay, let's look at the one here. The answer is the top structure. Why is it not the bottom? That was the question. What does this mean? Let's do it from scratch. What does that typically indicate? We've got 4 aromatic H's, pair of doublets. That's classical for this. Okay? We can confirm this by looking in the carbon NMR. No matter what's here, different or same. Well, if it's the same, you only get 1 carbon signal. If it's different, how many would you get? 4. And we got 4. Okay? That answer does depend on if these are the same or different. We can confirm that a bit later. Look down here. We got peaks at 4 to 5. How many DUS do we have? Do we get formula?
Yeah.
Yeah.
How many DUS? 4. Well, they can't be a double bond because here's your 4 DUS. So these are not alkene. Alkene would be more like 5 to 6 anyway. So these are saturated CHs. Okay? But the fact that they're at 4 from beyond tells us what about these carbons? Probably bonded to oxygen. Do we have formula?
Yes.
Is there any other heteroatom in this compound? Just 2 oxygens. Okay? These carbons are bonded to oxygen. That's why these H's would be downfilled. It's a CH2, most likely bonded to the oxygen in our formula, and that's it. It's isolated. Okay? This is a quartet 2H. This is most likely bonded to an oxygen, CH2. What would make it a quartet? Bonded to a CH3. Quartet, but it's also downfield, indicating it's probably bonded to oxygen. A singular 1H, D2O exchangeable. What does that mean? There's your OH peak. Okay? Do we have that in the IR? Yeah. It's like an alcohol. What do we have here? Triplet 3H. Well, that must be this guy, because if you got this, it's got to have a peak. Would that be a triplet? Yes. 2 H's next door, triplet. All your fragments are on the board. I got 3, you got these fragments. Okay. Do I just want to put an OH here? Why is it not that? What type of information was given in the top? Positive Jones. Now, we didn't clarify in class. A phenol could give a positive Jones, but we didn't even say anything about phenols. Phenols can be oxidized, but they don't give the same products as a saturated alcohol. The fact that it's a positive Jones tells us what, if we look at a regular alcohol? Primary, secondary. So we certainly do not want to show a tertiary alcohol, unless there's also a primary alcohol in the structure. Okay. There's another chemical test that you've seen in the workbook for phenols. Somebody?
NaOH.
Soluble in?
NaOH.
Soluble in sodium hydroxide. Okay? A phenol would be, but a regular alcohol would not be. Okay? If I gave that data here, I would tell you that this compound is not soluble in sodium hydroxide. Of course, it wasn't given. And these answers, neither one of these is phenols. I'm not sure how you rule out a phenol. Maybe there's other reasons. But we don't want to put the OH on the ring. Okay? That is, we need to put these on the ring. Well, you only got 2 others, so one of them has to be that fragment. Okay? Hold on. How many oxygens in the formula?
2.
2? I've got 3 oxygens up here. So one of those is a repeat. Well, this has got to be on O. That's got to be on the O. So one of these has to be an OH. This OH must be one of these. The question is which one? Well, it can't be this one, because if it was, that would just be ethanol, and you can't put anything else. So this must be that. And now we only have 2 fragments. Now you put one there, and you put the other one here, which is CH2OH. That's all you can be. And that's the top structure, right? Now, why is it not the bottom? Well, here's why. Because look, here's your, we got a triplet and quartet. Okay? Quartet 2H, triplet 3H. We've got that. The difference is, though, this is not next to oxygen. This would be about 2 to 3 ppm. Actually, it may be closer to 2. But our quartet here is 4.
So it's just because it's more down.
And that's a very critical point. If it's going to be down at 4, the carbon is bonded to, look at your table, it says bonded to an X. The X being oxygen, halogen, nitrogen. Obviously, it has to be only oxygen here because we have formula. That's the critical thing that but it's actually something that's often missed and forgotten about. So I'm glad you asked. Okay. Peak position there tells us that it's bonded to oxygen. Were there any questions, other questions about this? Also, look at here. This guy is between 2 oxygens in your structure. I would expect that to be like 5 or even 6. Now, that's not going to be the table because they're not going to show you something fancy like this. That would be a singlet 2H, assuming no splitting. Do we have a singlet 2H? And it is a little bit further on downfield, so it's okay. It's not that bad. That's the main thing there. We need an oxygen here. Okay, very good. Last questions about the material before we begin new material. One thing that I've seen has come up. Epoxides. Let's look at the epoxide handout. The page right before the epoxy glue. Maybe we didn't do one of these in class.
Yeah, we didn't do a lot.
We didn't do what?
The last 2. Styrene and then the other technology.
But we did this one, yeah?
Yeah, we did the first one.
Okay.
The form, the top side of the NH.
Which carbon is the ammonia going to attack? Top or bottom?
Bottom.
Why do you say bottom? Because I've been here. Plenty of people tell me and acting like it should be the top. Did we make it clear that this should attack the bottom carbon?
We just tapped it. Because it's less of
I would argue that it was clear because if you look over here, mechanism is always SN2 with strong nukes! Exclamation point. I'm getting people who are saying it should be SN1 in this case we're looking at. I'm getting people who are saying that, where are we at? I'm getting people who are saying, but this is a possible tertiary cation up there. And then saying, well, should we be doing SN1? No. Because you only have a choice like that when you're under acidic conditions with weak nucleophiles. Once we got to strong nucleophiles, we no longer have a choice. Strong nucleophile is always SN2. And if it's always SN2, which carbon are you attacking? The more substituted or the less? The less. Weak or strong nucleophile?
strong.
Now, amines are not anions, but we've always classified them as strong. They're strong enough to be strong. Certainly, where's the acid? You would only protonate and ionize to give the tertiary cation with acid. To protonate first and ionize. There is no acid. Of course, you cannot have acid with a strong nucleophile. This attacks here, opens it up from the bottom by an SN2. Okay? Just like a Grignard would, because a Grignard is a strong carbanion. Do this, I don't think we did this one here. MCPVA, what do we get? We're going to get the epoxide. What type of stereochemistry do we have? Well, we only got one chiral carbon. What's it going to be here? Be racemic? That is, you can draw one of the bonds back and then draw it again with one of them forward. I would probably draw that bond back and then draw it forward. Those would be your two forms. Okay, of course we should know that. Now we come in here with this strong nucleophile. Where are we going to attack? Right here, kick that off. What do we get? By the way, this is not a benzene ring. We kick off the oxygen. We now have the nitrogen bonded there. We didn't magically lose any H's. All we did in our mechanism is we make a bond between lone pair and carbon, kick that off. That bond was made, that's a positive charge. It's still racemic here. There's no stereochemistry there. And H plus transfer. You have a base, you have an acid internally. The acid-base reaction is going to happen internally. H plus transfer. Just make that neutral and have your amine. Okay? And your product, this will be racemic. There'll be two forms there. Okay. I just had too many people going the wrong way on that. Question, guys?
Can you go over finding the coupling constant on that problem in the NMR packet?
What value did you come up with?
3.6.
3.6? Very good. Very good. Make sure everybody can hear you.
In that example that we just did, would the H and the moved for the oxygen, or the oxygen, would there be like H plus transfer?
Yeah.
I can't really hear you.
Would there be H plus transfer? So the H from the nitrogen?
Yeah, we said that. Right, H plus transfer? I mean, I thought we did. I'm not trying to be whatever, but
We did. This might be hard to hear.
I have a question. This is probably reading too deep into it, but since it's the ammonia is basic, right? So since it's in a base, we need to do the pKa.
wait, what?
Like, could it shift another one? I'm just thinking about the hydrogen transfer.
Yeah, this becomes everything.
Are you saying, will that take it instead of that?
Kinda,
No, this is
yeah.
more basic.
Okay.
If you look at your pKa's, it's more basic.
Okay.
It's always good to consider pKa's. That's going to be an alcohol. Alcohol's pK about 16. Amines have pK about 10. Okay? That is, this protonated is more acidic than this protonated. So it's correspondingly, this is more basic than that. Think about it. Yeah, your pKa's do it rolling. And if you assess them, you'll see that we're going the right way. Other questions?
Could you possibly work out the coupling constant problem?
Coupling constant problem, that would be the NMR packet.
Yes, I think it's
Right here, 3.6 hertz. Here's your doublet. Coupling constants are given in hertz, not ppm. The hertz is the width between your two signals. Coupling constant is the distance between your two signals. Right here is the distance in ppm. The two values are given. The gap between the two values is to do this, subtract one from another. Okay? If you subtract one from another, you get, this is the difference in ppm. 0.012 ppm. That's how wide it is. But how do we convert that to hertz? Well, what is ppm? And this is where we'll have to end. Good place to end. ppm is a little bit hard to define. We didn't find it up front. ppm is parts per million. Okay. Different NMRs can have different magnets, magnet strengths. Okay. Actually, the stronger the magnet, the better your NMR is going to be. You don't have this in IR. Okay, it's all constant. Bigger the magnet. The bigger the magnet, the bigger the gap between your alpha and beta states. And the bigger that gap is, the more sensitive your instrument will be and you get better data. But look, if we look at our gap again between alpha and beta, here's your magnet strength. Now magnets can be quoted in Tesla, but they're usually quoted in the operating frequency for the proton. And you have something like a 60 megahertz NMR. This correlates with magnet strength. It's not Tesla. This is the approximate frequency of the protons for the given magnet. If we go to a bigger magnet, we may get something like 300 megahertz. That is, now this is energy. This is energy. But of course, energy can be converted into frequency. Higher energy, higher frequency. And this is frequency, hertz. Higher energy, higher frequency. Now this is a stronger magnet, it's better. But look at the problem here. If one researcher used a small magnet, the delta E for a given proton is going to be small. And thus we would say that a certain frequency of light was needed for that proton. Well, this person over here is using a bigger magnet. Its delta E for the same proton is going to be larger and thus a different frequency. So you get one answer with a small magnet, you get another with a large magnet. Well, there could be a variety of magnets. Everybody gets different answers. Well, that would be nebulous. Then nobody will ever know what the answer is. So you have to have some consistency. The ppm gives you the consistency. Now ppm, this is 1,000,000 hertz. What is a part per million of 1,000,000? Think about it. If you have 1,000,000 marbles right here. If I said come up here and take 1 part per million, how many would you come up here and take? 1. So a ppm of 1,000,000 is just 1. So a ppm of megahertz is what? Hertz. Okay? So 300 hertz is 1 ppm of this. Well, what's 1 ppm of that? 60 hertz. Okay? This is 1 ppm of that. Now look what's constant. Both of these are 1 ppm. Now everybody's quoting the same value and nobody's confused. Okay? You're not going to get this from my quick explanation, but hopefully you get the gist of it. Now look at here. I told you this is a 300 megahertz NMR. Thus every ppm is 300 hertz. What does that mean? We don't actually plot the hertz. But what it means is these H's resonate. If this was 2 and this is 3, these resonate 300 hertz, no, 300 hertz. 300 hertz more downfield than this. We don't call it 300 hertz, we just call it 1 ppm to make it consistent. Basically, we just multiply this by 300 and we get 3.6 hertz. You can think about it. Obviously, you did some reading, and it's all explained in the textbook. Here, a ppm would be 60 hertz. Here, a ppm is 300 hertz. And we get the consistency. Okay. Last question. We need to move on to new material. I'd prefer to have test on Monday. Any objections? No. Any objections?
No, please, for the love of everything that's good in this world, do not make an objection, please.
Okay. All those who want to have test on Monday?
It doesn't matter. Shut up. Dude, this is life.
Who wants to have test on Friday?
Seriously?
Are you guys kidding me? Are you kidding me? You have more time to study. You can study all day Saturday. No.
Hey, this is democracy.
I've always had test on Super Bowl Monday for 15 years. Because we started on the very odd start. That's why I'm considering this.
Please.
Monday.
Monday, please. We have a cell test.
Definitely Monday.
Please.
We could have it on Friday. I think you'd do better if you had it on Monday.
Yes.
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 If you don't want to study on Sunday, well then act like the test is Friday and study.
Yes, exactly. Thank you. Come on.
Okay? I'd rather have time over the weekend to make the test out. Any objections? No. Too bad.
We can say that argument if that's not much.
Oh my god.
My main reason is because you have another test on Friday. Okay, the number of you do. That's the only reason. If it wasn't that, I probably wouldn't be moving it. But that is a reasonable argument. I wanted to see if the other would move it. They did not move it, so I'll be aware of that. Okay, guys, I need to move on. If you have any concerns, let me know. Okay, aromaticity. Test 2 material is, we're going to start looking at the aromatic ring. Benzene ring, benzene chemistry. Our lab next week, we're doing a halogenation of sulfanilamide. Halogenating the aromatic ring of that. Sulfanilamide was the original sulfa drug. Okay. The lab we're doing this week is a worksheet, not the report, as I said before. Okay, that's due next week when you come to lab, the worksheet. Any questions about lab? Today we'll meet here and we'll do a quick NMR problem for practice. I think we're ready to begin. There may be other things to say. We have 2 handouts. One was golden, one was white. One was some warm-up questions. Those are semi-advanced, but they're hopefully of interest. They will address principles. Please be looking to work those. I think we'll go with the white. The gold is going to be more of our precise outline. Back to the white. There's many more aromatics than just benzene. We also have aromatics with heteroatoms. For example, right here. This is a pyridine ring. We have the nitrogen as a part of the ring. So only 5 carbons, 1 nitrogen. Because it has the heteroatom, these are called heterocyclic rings. Heterocyclic. There's numbers of these. Many in drugs. Many of these drugs you're familiar with. We can have different size rings. This is a 5-membered heterocyclic ring known as thiophene. It is aromatic. This here, fused to this, is a 6-membered ring. The nitrogen, or this piperidine. That's not aromatic. We need to make sure we understand what an aromatic ring is structurally. We will also see that we can have compounds called anti-aromatic. Aromatic compounds are particularly stable. Anti-aromatic compounds are particularly unstable. And actually, there's not many of them. But we need to know how to structurally see that something is aromatic versus anti-aromatic. Most of these names you do not need to know, although they're pretty common, be useful. We will see 1 or 2. We'll see pyridine a good bit. I'll mention thiophene at some point. Parole, there's Lipitor. The main ring in this here is Parole, $1 billion drug. Make sure we understand why that's aromatic. Intro to benzene and aromaticity. Benzene is the granddaddy of all aromatics. Formula C6H6, 4 degrees of unsaturation, boom. It's a liquid at room temperature with a boiling point of 80 degrees Celsius. That's its lower boiling than water. It's actually a pretty darn good solvent. It looks like it would be nonpolar. One thing we don't talk about at the introductory level is these pi electrons. Pi electrons are very polarizable. Even though we can't see the dipole on the board, it has some polarity from the pi electrons. They're a little bit more fluid than sigma electrons, and you get this temporary dipole. It's called polarizable. So it's a much better solvent than like hexane or cyclohexane, these pi electrons. So an advanced topic. Problem is, it's carcinogen. And so we don't typically want to use it. It's certainly not first choice. All right? And the industry just will not use it. Now, if you put a methyl on it, you have toluene. Toluene's much safer. Why? Well, we'll hopefully address that. Toluene we'll use in the lab this semester. Much safer. It doesn't mean it's safe. I mean, I'm not saying any chemical is safe. Ethanol is not safe. Okay. It's safer. And it's used in industry. This, no. Benzene was first isolated in about 1825. If I know who isolated it, pretty sure I know who it was. Who was big scientist back in this time? Came from Faraday, yeah. See, physics, but he also did chemistry. I think Faraday actually was big and isolated. Where did it come from? They used to burn well fat in street lamps. And then somebody along the way noticed that you had this liquid residue sometimes, or if you burned it in a controlled, you could distill out this liquid. And it was benzene. Well, of course, they didn't know it was benzene at the time. They didn't even... A carbon-carbon double bond was not even proposed until like 1860. Okay? 1825, all they knew is that they had this liquid. It had a smell to it. They could tell it was pure. They could tell formula at that time, but that was about it. You can go back and look at, what could they do at that time? All right, structure was not known until later. Okay, structure. Of course, this is just like organic 1. You could have did this then. Everything here you could have done then. All carbons are sp2, so they're all trigonoplanar. Standard bond angles are 120 degrees for trigonoplanar. Of course, you can have some slight variation from that, just like tetrahedral can deviate from 109.5. Right? So that's standard. There's your trigonoplanar. And so each H comes off in a precise. This we can call the sigma framework, because I'm only showing the sigma bonds. Now each carbon has a p orbital left over, right? sp2, p orbital left over. If this is flat on the board, the p orbitals are all 6 are what? They're all coming out. If I had 6, I'd all have them out, halfway back. Right? Now I can't draw them straight out, so I drew it separately, just the pi system. Okay, they're really all coming out. And each p orbital has 1 electron, right? Okay. Now, what do we do once we get those electrons? I could say pi bond here, pi bond there, and pi bond there. That would lead to this. Okay, you may not want to write this. Or I could say pi bond there, pi bond there. And that would lead to that. Well, which one is it?
It's a circle.
It's both. It's actually neither. Both are good. It's actually, well, if I'm just going to say there, there, and there, are you saying that there's no overlap between these two? Now, you might say, yeah. Well, as we learn when we talk about resonance and things, the answer is, well, that's not right. There is overlap. There's overlap all the way around. And we get into this delocalized bonding, which we call resonance, or conjugation. And that's really what we have going on. Electrons are all the way around here. Neither one of those are correct. It's actually like this. Okay? And these are actually what? 2 fake resonance structures. We can move between them by moving these here, moving these there, and moving these down. That would give you that resonance structure. Resonance structures are really fake. They're not the most accurate representation. We actually have a resonance hybrid. Also, if it was just double bond single, double bond single, double bond single, well, then you would expect the double bond to be shorter than the single bond. Isn't that typically the way it is? Well, that's also not right. We know that every carbon-carbon bond in benzene is 1.39 angstroms. They're all the same. It's not alternating short, long, short, long. If it did, benzene would look like this. It wouldn't be a perfect hexagon. It would be short, long, short, long, short, long. This is a purely isolated view that is wrong. Of course, we draw benzene like this all the time. But the same thing with the carbonyl. We draw carbonyls like this all the time. Of course, if you could look at a carbonyl, it would be more like this, with more of the electrons towards the oxygen. Okay, that's the old resonance thing. By the way, most double bonds, these are rounded off. A single is about 1.5. A double is usually about 1.3. This is somewhere right in between, which is like about a bond and a half. And indeed, we have a bond and a half between each carbon-carbon. But that's all was discussed in Organic 1 with structure, hybridization. Then we went into resonance. You just need to pull it together and make sure that you see that, see if there's any questions. Actually, when benzene was first discovered and people like Kekulé started working to figure out the structure, Kekulé thought that these were like isomers. And at some point he tried to isolate these. Well, not these, but below. Because those you really can't have isomers. These is what he actually did in the literature. Because he was like, in this structure, the pi bond is between the bromines, but in this one it's not. Kekulé spent a good amount of time trying to isolate those. He never could. Because those are not two different structures. The true structure is something like, now these dotted lines are often drawn with a circle, just to make it simpler. You put the two bromines out here, and this is all just through, you see it can't be two structures, it's only one possible. Now benzene is often drawn with a circle in here to illustrate that. I would recommend you don't ever do that. Because once we start doing mechanisms with benzene, how are you going to do a mechanism with a circle? So it's a shorthand which I never do. So don't tell me you ever see me with a circle. Okay? But you'll see that a lot because the electrons are completely localized in there. Now, how do you know these bond angles? Okay. Well, just to remind you, or if we haven't mentioned it already, we can do X-ray crystallography of compounds. And there's where you get all your bond angles and your bond lengths. Here's a compound we made, fluorination chemistry. We made this compound. We sent this compound to Emory to do X-ray. We don't do X-ray here. They send back the crystal structure. You can see that this ring is flat, but if this is flat, this one's sort of turned out a little bit from the board. Okay, and so that's how it is. You can see other features about the structure, but they also give you a list of bond lengths and stuff. If you focus it on the benzene ring with the chlorine, which is over here, each carbon is labeled the C1 to C2. C1 to C2. Bond length, 1.384. Previous page I said about 1.39 for a standard benzene. Okay?
So 5 after.
That's probably the variation in the 4. I don't know exactly, but then what else was here? Basically, this is just pointing out that, again, a lot of these structural features can be confirmed and obtained from X-ray crystallography. Okay? And of course, something like this, if you have questions, ask. It's not something that I'm going to spend a lot of time on, but maybe it'll generate some interest. Okay. We'll see how far we can make it. Well, this is introductory, so I'll move through it quickly.
What was the therapeutic target of that compound?
There really wasn't any. That was just some fluorination research. Like what was unique there is we were able to get 3 fluorines there. We only expected 1. Now, maybe we can explore some biological activity now that we know how to make the compound. Okay, aromaticity. We'll give a definition and then we'll modify that a little bit as we go. It's going to be an unusual stability as a result of full cyclic conjugation. We talked about the full cyclic conjugation is there. That leads to a particular or an unusual stability. The cyclic conjugation does. Okay. What do I mean by unusual stability? We'll look at some examples. What are some experimental evidence to support this unusual stability? By the way, what was A? Something about bond lengths? Bond order. Well, the bond lengths support the idea that we have this conjugation. I mean, is it single bond, double bond? No, it's 1.5. The bond length, the bond order is 1.5 approximately. What type of evidence do I have for that? I showed you an X-ray crystallography. That's experimental evidence that supports that. Okay? What type of evidence do I have about this unusual reactivity? Well, I haven't stated that. The stability kind of goes with the reactivity. It has unusual reactivity. Let's look at this topic. For example, if you react benzene with bromine, in organic 1, you might think, well, we'll brominate one of the pi bonds, and we'll get a trans addition, just like we did in organic 1. Maybe you could do this 3 times. This would be an addition reaction. It doesn't happen that way. These pi bonds are not alkenes. And we said that in organic 1, right? We said we will not react benzene with those reagents. Okay? Instead, if you react benzene with bromine, first of all, if it's sluggish, then you have to include a catalyst, such as iron. Now, regular alkene reacts with bromine instantly. Benzene is slower. Benzene itself is. Iron catalyst, we'll talk about this mechanism. But you don't get an addition product, you actually get a substitution product, where one of the bromines has substituted for one of the H's, and you produce HBr. That's the fate of the other bromine. So it's slower, and instead of addition, you get substitution. So I'm calling that sort of unusual compared to alkenes. We will be doing this mechanism. This would be called an aromatic halogenation. And next week in lab, you'll be doing an aromatic halogenation. You'll be using some unique reagents. Look down here. We know that alkenes can react with osmium tetroxide, alkene oxidation, KMNO4. Well, guess what? And if they do, maybe get like a cis diol. Well, guess what? Benzene doesn't react to begin with. What does that tell you about benzene compared to an alkene? Certainly it's less reactive. Why would it be less reactive? It's more stable. Another way to put it, if you want some simple language, it's happier the way it is. I'm quite happy being benzene. It's quite stable, quite happy. It's harder to get it to react. Now you actually can't hear some sophisticated ways, but I'm not going to talk about it. Okay? This is an unusual stability. This is some evidence. I'm not just making a statement, I'm showing you some evidence so that we know in lab. Here, why does it do substitution and not addition? Because by doing substitution, it maintains the conjugation. Here, we've lost the cyclic conjugation. We still have conjugation of the 2 alkenes, but we no longer have the cyclic conjugation. The system wants to maintain it, because it's a very favorable thing. See that? It wants to maintain. And very rarely will you destroy the aromaticity. There are times when you can. Usually it's going to be preserved. Okay, what is some more data that we can look for to say that something is aromatic, it has this stability? Another is heats of hydrogenation. We looked at this in organic 1. If you hydrogenate an alkene, something like this with like palladium or platinum, you can reduce the double bond by adding H's, alkene to alkane. This is going to be exothermic, right? Because we're replacing a pi bond with 2 sigma bonds. That's the amount of heat given off per mole. Now if you take this guy and do the same thing, you can reduce both double bonds. You get this much heat. Note, this is not exactly double. Double of that would be what? 336? I mean 236? Not quite double. Actually, I wish there was another one up here. What if we had the 2 double bonds like that? Which would give a higher heat of hydrogenation? This one. Why? They're both going to the same place. Both these would go to that. Which one sits higher to begin with? This one sits higher. Why does this one sit lower than that one? Because at least the 2 double bonds are conjugated. Conjugation makes it more stable. That means it's lower in energy than this one. This one would give more like 236, double. This one gives a little less because it's conjugated. Let's look down here. What if we put a third one in, make it benzene? First off, you've got to use a very special catalyst. Your simple ones don't work. You have to start using the expensive ones like rhodium and ruthenium. Or you can get away with super high pressure. Okay, it's less reactive. That's one thing. Also, when we go here, look at what we get. 3 double bonds, but we actually get less energy out. That's because this guy actually sits lower than these 2, where it starts with. Now, it doesn't sit as low as that one. Why does it sit lower than these? Because once we put the third one in, now we have the magical cyclic conjugation that really stabilizes it. Makes it sit lower, and since it sits lower, when it comes here, it doesn't have as much energy to give off. So the heat of hydrogenation can help tell you something. Okay? NMR. We said aromatic is about 7 to 8. If this was just a simple old alkene, like a triene, it wouldn't be 7 to 8. It would be in the alkene region, which is 5 to 6. We can point this out more. But this position tells us that it's aromatic. It has this nature. Right? Please don't just call this a triene, because if it was a triene, the signal should be in the alkene region. So that's a little more evidence. Okay. What we're going to be looking at is molecular orbitals. Because to really understand it further, we have to get into molecular orbital theory. So the next couple of pages actually give you a summary page. Free information, no charge. I think I call it keys to MO theory or something. Okay? It's free information, okay? Please be looking at some of that. Okay, I know we got tests coming up on Monday. We will be doing this on Friday. And if you want to be able to follow along, we can start doing some reading. Molecular orbital theory, thank you.